I'm Tom Siewert, and I'm going to give you a presentation about our planet. How unique is it? Is this one of many of thousands possible Earths around the galaxy with other life forms going on, or is there something really special about our planet? It's really based on a couple different sources. One of the sources is a book called The Privileged Planet by Guillermo Gonzalez and Jay Richards. There's a second book, Case Against Accident and Self-Organization, that also goes through some of the uniqueness of Earth, and I put that in there as well. But both these books are a couple decades old, and so I've added some recent data on exoplanets to help understand what's out there and what we have recently found. Really going to do this in 4 pieces. I'm going to start with a secular view of what our Earth is like, and then I'm going to talk about the special features of Earth, and then also its location, where it is in the solar system, where it is in the galaxy, and then some other little attributes that are just amazing. So let's start with the secular view first. What are some of the early viewpoints? What did people think about the Earth before we had telescopes, etc.? Start with Aristotle and Ptolemy. What do we know about it? Well, when you look up at the night sky, you see things moving. You look up at the day sky, you see the sun moving. Sometimes you even see the moon there. We might see Venus at morning and evening. They came up with a model that you see at the bottom there. The Earth is at the center. The sun, the moon, planets, and stars all rotate around it. The Earth is motionless. If you're moving, if you're on a boat or if you're on a horse or something, you feel wind, you feel motion. Well, it must be motionless. There's no wind blowing, things fall straight down. So that makes sense that Earth is at the center, motionless, and any rotation of sun and moon and other things are relative to us. Now, Aristotle and Ptolemy had several points of view. Here's a delayed motion shot of what's moving up there. They see the stars rotating together, although there possibly is some motion if you observe for a long time. There were other viewpoints as well. We see inside that motion, the planets are moving separately. But why do Venus and Mercury seem to move backward at some times? That was a strange little situation. We'll come back to that in a minute. Other viewpoints by other people. Pythagoras is a famous Greek that we know. He thought that the Earth was a sphere. Good insight there. And they did things that were pretty interesting. They would dig wells, and you could look at the sun going down in that well and measure angles, and from that they could come up with an idea of how big it was and its shape, and he thought it was a sphere. Other people like Plato thought it was a cube, but also Socrates had another viewpoint. He thought the Earth was spherical in the middle of the heavens, but it's bigger than we expect, vast, and the known world is only one of many little hollow places on the surface of the Earth. There's one more Greek, Aristarchus. He thought that the Earth rotates on its axis around the sun. That explains Venus and Mercury's motion. That makes a lot of sense to us today, and we take that as the viewpoint, but at that point, it didn't seem to make sense because we didn't feel wind. So the lack of wind was the compelling idea. It swayed most people to the views of Aristotle and Ptolemy. But why do Venus and Mercury move backwards at times? When people tried to make a model of the solar system, they ended up with something very complicated, and it required epicycles and equants. What are these? Well, epicycle is effectively a motion around a circle where the point you're looking at is beyond the circumference. Imagine a locomotive wheel. The face of the wheel rotates on the track, but the flange, the part of the wheel that keeps it centered on the track, obviously has to be bigger, And if you would look at the motion of a point on that flange outside of where it touches the rail, it actually moves backward when the wheel comes at the bottom. And when it comes up to the top is moving faster than the top of the wheel. So that's really a simple explanation of an epicycle. So really, the status of the model of the world at 1500 AD was based on what we saw from the Greeks. However, one Arab, Abu Sa'id, actually invented an astrolabe. That's a model of the solar system. You see it symbolized there in the picture. That's based on what we see today. It did not require equants, and it did not require these other special motions. However, his work was in Arabic, so it's not well known in the West. What we do know in the West is Nikolai Copernicus at that time. He said the sun is the center of our solar system, and planetary motion is in reference to the sun. And, of course, the Earth rotates on its axis daily and around the sun yearly. That's the simplest explanation for Venus and Mercury and the precession of the equinoxes. He published this simple idea in a manuscript about 1510, but the final manuscript was not published until after his death. And one quote he had, which is really quite insightful: "How astonishing if within the space of 24 hours the vast universe should rotate rather than its least point." Now we move to Galileo. We're quite familiar with him and the statements that he made. He agreed with Copernicus and diverged from the Greek view on the solar system, but also on other topics. The Greek thought that time was kind of a dreamy thing and we weren't really experiencing it. Copernicus and Galileo thought that time was very linear and fundamental. Also, they thought that manual labor was ennobling and nature was not to be revered, which goes against the idea of the Greeks. Further, he was quite a scientist and made contributions to astronomy. With a telescope, he discovered Saturn's rings and Jupiter's moon. He made contributions to physics and to engineering. However, he had a conflict with the church, and that's partially his fault because he mocked the Pope and demanded immediate acceptance of his views. Well, since that time, we've gone on and taken that Copernicus concept farther. Now there's something called the Copernican principle. Since Earth is not the center of the solar system, we have no special place in the universe. Now, Copernicus and Galileo would not agree with that concept. They still had a great view of God being in control of the world. Next, we have something called the principle of mediocrity. Okay, since the properties and evolution of the Earth are not special in any way, the processes that led to life on Earth are likely to have occurred on many other planets. And of course, that leads to the search for life on other planets. So some of the things we have since that time: we have Edwin Hubble, which he determined that what we thought were clouds of dust way out in space were actually distant galaxies. Thus, the Milky Way is just one of billions of galaxies. So we've got billions of stars in our galaxy and billions of other galaxies, billions times billions, tremendous number of stars and planets out there. And of course, we've heard that from Carl Sagan and other astronomers. Then the next question is, well, if there's other people out there, how many are there and how would we find them? Well, there's something called the Drake equation that tells us who is out there. It's an equation that quantitatively gives you values. The N is the number of civilizations. R is the rate of star formation. F sub P, the fraction of stars with planets, and then those that could support life, those that actually have life, those that develop intelligence, those that communicate, and then the time that that civilization would exist and could communicate. This sounds very scientific and very wonderful. I would agree that the first couple terms, star formation, we get some idea with telescopes. fraction of stars with planets, that's a lot more difficult. And as we finally go down in the list, you just have to guess. You can guess low, you can guess high. And so that's one reason why this equation is possibly one of the most famous ones, for it has the greatest uncertainty. The true answer is hard to determine. That's why people are searching the sky. We'll never get the total answer because it's just unknowable. But there are implications. Carl Sagan thought there might be billions of other civilizations. And other people have good quotes. Robert Jastrow said, "The universe is populated by innumerable Earths and perhaps innumerable forms of life." Because of this, we search for extraterrestrial intelligence in the galaxy. Also, we search for extrasolar planets around nearby suns where life might exist. So with telescopes, there are several techniques we can use to find motion of planets out there, and you'll see we have some lists of some of the ones that are found. This is one reason why we have so much science fiction out there. You know, perhaps 10% or 15% of book sales are science fiction. And of course, there's TV shows. There's a tremendous number of innovative stories out there. And people have extrapolated, what does this mean for us? How many civilizations are out there? I have this quote from Hitchhiker's Guide to the Galaxy. Earth is an utterly insignificant blue-green planet orbiting a small and unregarded yellow sun in the uncharted backwaters of the western spiral arm of the galaxy. Well, that's one view. Another one, you can go online to the SETI website, and there's as many as 300 million potentially habitable planets. But not everyone is quite so optimistic. Enrico Fermi has a very famous quote, "But where is everybody? Why don't we see them?" Now, this has led to various things. One is the weak anthropic principle. It says, we are here, so conditions must be this way. Also, with a limited basis for comparison, in other words, we can't go and explore all the other stars and planets, our world doesn't seem that strange. Of course it's this way. So you can take a very optimistic view of lots of civilizations, lots of other life forms, and of course that keeps the science fiction industry going. On the other side, is there an amazing fine-tuning of conditions that allows us to exist? And how did that fine-tuning occur? Well, one postulate, it's by design. So let's compare Earth to the features of other planets to learn how likely these situations exist elsewhere. One, water is a key factor in life. It has high heat capacity that moderates the temperature on our planet. It supports the largest creatures on Earth. It has good solubility for minerals and molecules that allows these things to transport through the water. It's an excellent media for chemical reactions, and it has high surface tension, which allows sap to travel to tall trees. If we didn't have that, we would only have maybe moss or something like that. Also, it has multiple phases. It has vapor, which forms rain. It has solid, so it floats on the surface of water. Otherwise, lakes and oceans would freeze solid, and in summer we'd only have a little bit of water floating on top of the ice. And obviously that would not allow fish or plants in water. It seems to facilitate tectonic plate motion, which allows minerals to recycle in the Earth's crust. Very importantly, it is transparent to light, and that allows sea creatures to exist and see. It also allows light from the sun to penetrate and plants to grow. One very positive factor is it'll quench fires, and it has low viscosity, which allows it to flow back to the sea. And in our bloodstreams, it allows the transport of nutrients and things through our bodies so that all our cells are furnished with what they need and waste products are taken away. There's a sensitive balance of land and water. In the top right, we look at a planet that's too dry. There's no water cycle. We can't transport material. Maybe there'd be a little growth right along the edge of the lakes or water, but you would have barren deserts. On the other hand, if we had a planet that was almost all water, there'd be no mining for minerals and no fire. It would be very hard for us to make technological progress, and there'd be no fuels. So there really is a sensitive balance of land and water. By changing that balance, change the character of life. In the bottom there, we see some of the unique environments that are on Earth, which are kind of extremes of that balance. We have alpine tundra, Arctic tundra, and deserts. Another important factor is the moon. A large, close moon causes large tides, and that contributes to ocean currents, which keeps the north latitudes warmer. They mix nutrients and allow life in the tidal zones. Also, the moon helps shield Earth from some impact events. After all, what caused the craters on the moon? Our moon has other features. It's very large in comparison to other moons in our solar system, and that stabilizes the axis of rotation of the Earth. On the other hand, Mars moons are much smaller, so the tilt of its axis changes substantially over time, leading to major climate shifts. Also, the axis of rotation is important. Our 23-degree tilt gives us seasons. A much higher tilt would lead to one pole being too hot and the other being too cold. Without the tilt, we would have no rainy seasons, and both poles would be colder and the equator hotter. Okay, how does this compare to other planets in the solar system? Most of them have the wrong light intensity, which would not allow plants to grow. Either too much light, which would burn them, or not enough light to allow them to grow. Too hot or too cold. So basically we're in the Goldilocks range, just kind of the right temperature for life to exist. And we don't know of other forms of life that could tolerate. You know, science fiction talks about things based on silicon and things, but we have not been able to find any of those on Earth, and scientists can't seem to create life based on that either. There's no or little water on these other planets, at least in liquid form, which is a key factor. They really don't have a breathable atmosphere that we could use. The strange tilts cause extreme temperatures, and they don't have precession of axes, so thus there'd be no seasons. Most of the others have gravity that are too high or too low. Too high, and you can't really have large creatures. Too low, and you can't retain atmosphere. If you don't have magnetic shielding, you have a lot of cosmic rays coming down and causing damage to cell interiors. Also, most of them have the wrong ratio of metals and minerals. We need to have the right amount of those things just for technology to occur. Well, what have we learned about other planets outside the solar system? Here is some recent data from NASA looking at other planets that have been found outside our solar system. There's a little green dot to the lower right. That's the Earth condition. If you go down at the bottom scale, you'll see an orbital period of 365 days. And if you go to the left scale, you'll see the size relative to Earth is 1. Of course, Earth is that standard. But notice how much they go above and below that. So there are planets that are much smaller, perhaps 20% the size of Earth. On the top, there are some that are 40 times larger. So on one side, at the bottom, you probably have very little or no atmosphere. At the top, you have too much atmosphere and such pressing gravity that life would have great difficulty existing and moving. If you look at the scale from left to right, Some orbital periods are only like 1 day. In other words, the planet is moving around that star in 1 day. To the right, it's tens of thousands of days. What does that mean for the condition? Well, you can see it on there. Some are rocky, some are ice giants, some are cold gas giants, some are hot Jupiters, some are lava worlds because they're very close to the sun. There's really nothing with Earth conditions, much less having the features of what we need. We don't know about the resources on these planets. We just know how fast they're rotating and the distance from their sun or their star. We need certain things. We need about 27 elements for human life. Obviously, we think about oxygen. Too little, we'd suffocate. Too much, we'd have extreme fires. So there's a range. Carbon. We need carbon because that's the best way of forming complex molecules and energy sources. If you go online to look at different elements that are formed or various compounds that are formed from elements, there are many, many times more compounds formed of carbon than all other elements together. We need nitrogen to dilute the oxygen in the air and provide the density of the atmosphere. It also keeps those fires from getting out of control. We need hydrogen. That's a major component of water. Also, we need that in our bodies. It's what fuels the sun. We need iron. Just look at your vitamin pill contents. Iron is a key part of our body. It's also a key component of hemoglobin that allows us to transport oxygen. We need magnesium. It's a trace element also in our bodies. It's related to the calcium in our bones. It's also an important thing in chlorophyll. And it goes on and on to many more. But it's not just these elements alone. We have stored plant reservoirs are critical to our way of life. Wood itself is stable for hundreds of years. How far would we get with straw or hay for fuel or construction? Also, coal is very important. It fueled the Industrial Revolution and produced electricity. Natural gas heats most houses. Petroleum products provide gasoline, plastics, and asphalt. What would our life be if we didn't have these stored plant reservoirs? They're critical to our way of life. Early, we used candles, oil lamps, and torches for light. And wood or charcoal fueled the first refining of metals like copper and tin, and alloys such as brass and bronze. These resources are critical to our way of life. The high energy density of coal allowed us to make iron and steel. These fuels reduce calcium carbonate to lime, allowing us to make cement. The stable storage of plants and grains allows us to feed ourselves over winter and through droughts. What would life be if we didn't have these stored plant reservoirs? Earth's core is very important as well. A molten metal core anchors the magnetic field. Also, radioisotopic heating keeps it molten and keeps crust warmer than it would be otherwise. The lower oxide density of our surface allows the continents to float over the core. And then we have tectonic plate motion, especially subduction. That's where the crust is pulled down deep, and that recycles the residue, the key elements that are building up on the ocean floor. Otherwise, we'd run out of nutrients. Another factor is the mass of the Earth. It has a major influence on the size of life here. Again, if it was too low of mass, we'd have less atmosphere, which have less oxygen for metabolism, more cosmic ray damage. If we had less oxygen, only very simple life could exist, on the order of moss or single-cell organisms. But if we had too much, that would limit the light to the surface. It would also prevent learning about cosmology. Well, how could we avoid that? Can we have life based on silicon? The element closest in features to carbon is silicon. However, there's very few silicon compounds indicating that's not a good basis for life. One type is silicates, like sand. They're very common, but brittle. Another one is silicones, which are chains of alternating silicon and oxygen molecules. They're flexible, but not as versatile as carbon. We use silicones in caulking around our windows, for example. Other elements seem to have even a poor basis for life. What about our location? Topic number 3. There's something called the circumstellar habitable zone. That's that blue ring around the sun there. If you're inside that or outside it, it's not as positive. Inside, it's probably too hot because you're too close to the sun. Outside, you don't have as much light density, so for plants. Also, it's probably a lot colder. Another important thing is we have a very circular orbit. That means during the year, we have a continuous heat input. The sun itself is very stable. So from year to year to year, it doesn't change very much. Otherwise, we'd be cooking or freezing. We have a very appropriate distance from the sun. Other stars vary in output by more than 20 times. So they're variable. They move and they change. That would not allow a life to exist. Also, the sun's output is centered in a wavelength suitable for photosynthesis. The band gap energy is very appropriate for the energy needed by chlorophyll. Also, that output penetrates the air very well. Venus is much hotter and very dense atmosphere. Mars has very little atmosphere, only about 1%. Other planets are even less hospitable. Other planets capture many comets and asteroids. We wouldn't want to be living there. Going to a higher level, we're in a very special habitable zone in the Milky Way. We're at an intermediate location from the center to the edge. The inner region has a massive black hole. Nearby matter is drawn in and it releases fatal levels of radiation. Also, that center region has more supernovas. Well, what about further out? Outer region is low in the metals needed for life. Finally, we are between the spiral arms, which have a higher concentration of supernovas. So we really are in a Goldilocks zone within the galaxy. Now let's look at other coincidences. Putting all the things we've seen here, all these features together, we have key factors all at once. We have the stable sun. We have the proper metallicity of heavy elements that we need for technology and minerals for our bodies. We have the other necessary elements as well, nutrients for plants. It's right-sized. It's the right temperature range. It has a large moon for rotational stability and producing tides. It has a circular orbit and the proper tilt. It has the optimal solar spectrum. We have tectonic plates which recycle key materials, and it has a molten magnetic core which deflects cosmic rays. It has optimal atmosphere. It has the right water and land balance. We have stores of fuels as coal and petroleum and natural gas. It has concentrated ores in ratios that are easy to receive, and it goes on and on. Let's try and put this into the Drake equation and figure out how likely life is. There's other coincidences. Life needs a habitable planet, but life is what makes a planet habitable. We need the oxygen that's coming from the plants. The plants have a way to recycle our CO2 back to oxygen. There's nested interactions and cycles all tied together. There's something in physics called the weak nuclear force. It's critically balanced between neutrons decaying too quickly. If that happened, we'd have no helium or heavier elements to use. On the other hand, it would also use up all the hydrogen, so we'd have no water. If the force of gravity were changed by 1 part in 10 to the 40th, that's 1 with 40 zeros behind it, all stars would be either blue giants or red dwarfs. Also, the number of electrons must be balanced to that of protons to 1 part in 10 to the 37th, or the electromagnetic force would overpower gravity. Finally, those who calculate things say a black hole cosmos, in other words, nothing but a black hole, is much more likely than ours by a factor of 10 to the 300 power. Wow, all these coincidences are amazing. Let's go back to the Drake equation again. We see all these factors in there. Well, perhaps the estimates would be a lot lower if more of these coincidences were factored in there and considered. Here's a quote from Fred Hoyle, famous astronomer, who says, "A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as chemistry and biology, and there are no blind forces worth speaking about in nature." So again, let me list the sources I used here if you want to go and look at them again. These first books are very interesting and they contain the details, more details than what I was able to include here. You see I've used an online source of the template, and also additional images were produced by Luke Petros. But the bottom line of all this is that random chance is not a reasonable explanation for the Earth's features. It just can't come about. The chance is just too little of all this working right. Millennia before telescopes were invented, the Bible said, "And God said, let there be lights." And it was so. The heavens declare the glory of God, and the sky above proclaims his handiwork. His invisible attributes have been clearly perceived. So the Bible really says there is an explanation for this. So, does this have implications for your life? What is your worldview? Are you counting on random chance making everything happen? Or is there a designer behind making everything work and come together the way it is? Thanks for listening.